I want to thank everyone for joining me today for this webinar on Introduction to Partial Least Squares Regression. Just a quick outline of what the plan is today. We are going to talk just about a little introduction into multivariate analysis in general, why we do it, what it means. And then we'll get into some regression modeling and a quick little course summary at the end. And there will be a couple of live demos using the unscrambler as well. So a little bit of history about multivariate data analysis. I'm sure everyone was used to, back in middle school and high school, everyone talks to you and says things like, you should only change one variable at a time when you're looking at your data. That's called a univariate method, and there are some cases where that is the case, where it works well, especially when you have low spectral resolution. Back in the day when you might have, say, filter wheels to bring out your spectrum rather than diffraction gratings or FT instruments. But one of the things that we've learned is that when you only move one variate at a time, you forget about what's happening in correlations between your variables. Okay, so in about 1975, that's when we started coming up with multivariate methods. Chemometrics came out of that, which is just multivariate statistics applied to chemical problems. At this time, it's very cheap to take measurements, but the experiments themselves might be quite expensive because you need to take many, many samples of things. And we needed adequate methods to handle that kind of data. So if we think about it, all real-world processes are multivariate. So if you think of something like the weather, there are a lot of factors that are affecting the weather or parts of the weather, like the wind, your air pressure, your temperature, your dew point, what season it is. If you just take a look at, say, your temperature, you don't get the full picture. You don't know if it's raining, whether you need your galoshes or your umbrella that particular day. And we also have many different sensors to measure those types of things. And one of the ideas too is that when you have all these different types of sensors, they're on different scales, so you need to have ways to combine this data in a way that makes sense. If you look at the univariate world, and this is very common, especially in process manufacturing, where you'll have a control chart. So you'll have a number of variables like temperature or pH that you're trying to measure, and you know what your target is. Say for your temperature here, your target is 30 degrees Celsius. Your pH target is 5.3, and you have some statistical limits around those that you know in a normal situation this is behaving accurately. So we take a look at this and it seems like everything is behaving as normal, but say we get some sort of output at the end and our product isn't coming out the way we expect it to. When you try to do your root cause analysis, when you look at your univariate situation, it seems that nothing is wrong. However, if we look at temperature versus pH in our multivariate view, we can see that there is clearly an outlier sample here. If we have only extended our univariate limits around there, it is not highlighted. It's too wide to detect a multivariate fault. And this happens a lot when your two variables under consideration are not actually independent of each other. When one changes, the relationship with the other one is affected as well. So if we are able to put multivariate limits on here, we were able to see where we have that outlier sample, go back and see where it falls in our temperature and pH charts, and we can have a better understanding of what's really going on in our process and where our sweet spot, where we really want to be to have good quality control over our system actually is. Another reason that we might use multivariate data analysis is in cases where it's very difficult or time-consuming or impossible to make a direct measurement. So you might have to do something indirect, such as measuring the temperature in a furnace load. There's no real way to put a thermometer in there and get an accurate answer because it will burst. However, if we take an indirect measurement, shine or measure the infrared emission coming out of that, we can use our first principles to understand what the temperature inside that furnace actually is. And these kinds of approaches and measurements often need a multivariate analysis approach. So what kinds of data are multivariate? There's all kinds of data that are multivariate, such as sensory data. So this might be in the food industry, for example. They might have panels, sensory panels that are tasting things. You might have instrumental analysis for this, say like your electronic noses, electronic tongues, and comparing that with consumer preference. That can use multivariate data analysis. Very common is multivariate data analysis in spectral and image data, especially near IR, due to the combination and overtone bands. And also just chemical data, raw materials analysis. When you're getting your raw materials in from your distributor, is it what they say it is? You can measure process variables, temperature, pressure, pH, conductivity, humidity, as well as end product quality measurements. So some of the motivation for your multivariate analysis of spectroscopic data. So spectroscopic methods, they provide insights into both the chemical and the physical characteristics of your samples. Now, sometimes those physical characteristics can be noise and overwhelm the chemical nature of what you are looking at. So you often have to do some sort of pre-processing and multivariate techniques to kind of pull out that very important information and minimize your noise. And again, as I said before, this is most common used in near-infrared spectroscopy, for that is one of the ones that is notoriously difficult to pull out information without any sort of manipulation of the raw spectra. So data analysis in practice. Keep in mind that your data analysis really is about 70% your application knowledge and your common sense. Data analysis is really an interpretation of the output of your data, and if you don't understand your application itself, it's not going to make a lot of sense. The remaining 30% is where your statistics and your mathematics come in, and that's where the unscrambler helps you with. So you don't have to worry about that part. You just need to know how and when to apply it and how to interpret it, again, based on your application knowledge and your common sense. So let's talk a little bit about regression modeling, and we're just going to do a little bit of refresher on what regression modeling is. So if you have a problem with no direct way of measuring it, so in this case, we've got these 3 balls. We don't know how much they weigh. We are really concerned about the weight of these balls, and we don't have a scale to put them on. So we think back to some of our first principles. How else could we figure out what these balls weigh? And we know that the expansion of a spring is directly related to the amount of weight that is placed on it. Well, we happen to have a few known weights that we can put onto the spring, measure it with a ruler, and come up with a model. So we can fit a line to these data points, and from that we are able to back calculate our unknown based on that model. Now keep in mind that we cannot extrapolate. So this model shown here is only valid if the mass of our unknown is between 1 and 3 mass units. If it is outside of that range, we cannot be confident that this is an accurate measurement because for some reason or another you may lose linearity. And we also cannot be any more accurate than our reference method. Here, our mass, we know it to the 10th place. We cannot know our new masses any more precise than that 10th place. Okay, so just keep that in mind when you're doing your own analyses. So again, regression analysis, when we collect data on a system, we assume that there is some relationship between our variables. We can plot those variables against each other. If they lie on a straight line, we say there's a linear relationship. You could also have a logarithmic relationship or an exponential relationship. That's fine. And there's different ways of modeling things that are nonlinear. So we're going to focus most on linear regressions today. So with a linear regression, we plot x and y versus each other. We fit a straight line to that data, and that's based off of a least squares analysis to try to minimize the error term. And when we do our traditional linear regression, where we look for our slope and intercept, we often ignore this error term. It is there, but we don't really report it very often. That's not the case in multivariate statistics. In multivariate statistics, that error term is one of the most important things that we put to say how good our regression model actually is. Because what we care about is when we predict new data is how accurate it is. And this error measurement gives us a way of phrasing how accurate our new results will be. So with partial least squared regression, which we're talking about today, the way it works is you have your X block of data. This is your independent data. This might be your process values. This might be your spectra that you collect. And you run a principal component analysis of that. And then you take your Y variables. So this is any of your analytical output, your quality measurements, things that you're trying to predict from your X data. You also do a principal component analysis of that. Then what we do is we plot those scores versus each other. So we've got the T1 is the scores for the X data, U1 is your scores for your Y data, and we look at the linearity between the two. Now, what PLS really does is aims to maximize that covariance between this to make this U versus T as linear as possible in each factor. So common statistics that we get in regressions is going to be our root mean squared errors. That's going to tell you basically the standard deviation of your differences between your predicted and your reference data. They're calculated, just the difference between the errors, squared divided by a degrees of freedom value, and then the square root of that. We also might look at a bias. This tells us whether we are generally predicting our samples more positive or more negative. You want that bias to be as close to zero as possible. And keep in mind this is not the same as the intercept or offset. What the intercept or offset is doesn't really matter. It's not important that it goes through zero. But your bias, you would like it to be as close to zero as possible. So that's saying that we are equally likely to predict either higher or lower overall. Again, we look at intercept, which I talked about. That is just where your fitted line crosses the y-axis. Again, it does not necessarily have to pass through zero. We do look a little bit at our r squared. It's not as important as many people think it is. You can have a really good error measurement and not a really great r squared. And what really matters in your regression is how well it predicts in the future. So your RMSEEs are really your kind of more important factors. Once you get that below the threshold that is acceptable for your application, then if you have two models that are otherwise equal, you might go and look at your r squared and see which one's more similar. One way the r squared is used is if we compare our r squared Pearson value versus our r squared. We want those to be as close together as possible. Okay, so the r squared, the general r squared here, is your correlation coefficient. It's like, what is the correlation between your data and a perfect line? The r squared Pearson looks at the amount of variation in your data that you're actually capturing. So that's why if we can get them as close together as possible, that means it's more reliable, assuming that you're not using a ridiculous number of factors. A little bit of a rule of thumb, depending on the type of your data you're looking at, if you get more than about 5 or 6 factors to predict your model, I start to get a little bit nervous. Unless you're in a field that has a wide number of variations, such as your agricultural field or biologic samples, there's just a lot of variations in your sample that are uncontrollable. And in that case, you might get out to more along the lines of 15 or even 20 factors. But most of your general, especially laboratory data, it should be, under 5 factors or so. Again, just a really high-level rule of thumb there for your use later. We talked about the root mean squared errors. You get different ones for different stages of your modeling process. The first stage is your calibration model, and then your cross-validation. These two tend to be very important. And then your RMSEP. So if you have an actual test set, which is the best way to test your data, then you want to use this, and this is that number that you report. But your root mean squared errors, keep in mind that they are in the same units as your original data. So if you're measuring pH, your error numbers are in pH units. If you're measuring conductivity, they are in conductivity units. A lot of times people get confused because you often have decimals, things that are less than 1. People tend to think that they are percentages, but they are not. They are in the original units, just like a standard deviation in your univariate space. So let's give a quick example, looking at some process data and measuring the quality of some paper. So what I have here is I have some process data measuring a number of things about paper that has come out. So we've got weight, we've got a type of ink, the brightness, how much light it scatters, the opacity, etc. And what our quality measurement is how much ink prints through. So how much, when you write ink on it, how much comes through the back end. And we're measuring all these things and we're wondering, can I use all of these measurements to predict this print through? Because maybe this is a difficult measurement to make, or it's expensive, or it's time consuming. So what we do is I can go under Tasks, Analyze, Partial Least Squares Regression, and I'm going to choose my training set. So I have this split into a training set and a test set. So we're going to build our model on the process data for our training information and use it to predict our quality. Now, if you take a look at your data here, you can see weight is ranging in like the 40s, something like ink is single digits, permeability is in the hundreds. If we put this data in directly without weighting it, the data analysis would tell us that this permeability is the most important thing, or maybe density is the most important variable just because it has a large value. So what we want to do is we want to come in here on our weights area and select everything, and we're going to weight it by this top one here. Make sure to click Update. What this will do is it's going to mean center and divide by the standard deviation. So it's a mean centering and scaling just to get all of our data on the same playing field, to get the same starting point. I'm going to do this as well with my Y data, and we can check our validation. In the Unscrambler, every model you build has some sort of validation to it. That's part of our philosophy for you can set your calibration data and you can model it perfectly using however many factors you need to do that. But when you put in new data, how does it perform? That's what really matters. It's not just can you explain the data you already have, but can you use that data to explain new data? And a way of making sure that that is possible is doing validation. So we're just going to do a cross-validation that's going to pull out a certain amount of our samples and predict them in. I have to change my algorithm because I did something else earlier. Your default will be NIPAL, so that will not be an issue in your case, unless you've changed it. And very quickly, we get a model. One of the first things we look at is our explained variance. And this is our Y variance. So we are explaining, let me get my data points on here. In two factors, we're explaining 87% of our differences in Y. That's a pretty good amount when you're looking at process data. And you can see when you go to a factor 3, you're barely getting not even really a full 1% extra information. So that tells me that's no more than a two-factor model. Another thing we may look at here is if we right-click, we can show our press plot. So this is looking at our root mean squared errors, how it changes by how many factors you include. So you want to choose a point where you start to level off. Again, this shows us two-factor model is probably as far as we want to go because we're not gaining any information, gaining any predictability by going to factor 3. So the next thing we want to look at is going to be our loadings. And I'm just going to go up here and show my labels. And we can see that in this loadings plot, print through the red dot, that is going to be the thing that we are trying to predict. And the blue dots here are all of the original variables that we were looking at. And so we can take a look to see which ones are important for predicting print through. One way to do that is just to look at your loadings this way. I also like to look at my correlation loadings. That puts everything on a unit circle. It gives me a little bit more understanding what's going on with my data. What these ellipses are is it shows how much the individual variables are contributing to a particular factor. So if we want to look on factor 1, which is going to be at our x-axis, anything that is between the two ellipses is a relatively important factor. It's going to be strongly captured by that factor. The variations in, say, opacity and scatter are strongly correlated with factor 1. Things like oil absorbance is not strongly correlated with either principal component or factor 1 or factor 2. So it's probably not that important to measure. In this particular case, we have only two factors. So things that lie inside this circle probably aren't that important for predicting print through. This is one way to help you do some variable reduction. Why are we measuring 15 things if only 10 really matter? So this kind of helps you with that as well. We can take a look at our scores plot, put our hoteling t-squared ellipse around there. This is kind of what we expect to see. Right now I have this set at a 95% confidence interval. That means that 95% of the time your normal data will fall inside the circle. We have a couple of points that are outside of the circle, but they're not very extreme, so I'm not worried about them being outliers. And then the other thing we look at is our predicted versus reference. Keep in mind, we need to make sure that we've set the correct number of factors here. In this case, both the software and our own knowledge allows us to choose that factor 2 is the correct one to use. So these will be our statistics for a two-factor model. And you can go through and see if there's any sort of outliers. We can put on our trend lines if we want to see what our regression lines look at. And the target line, so that's your one-to-one. You can see they're very close to that line. And we've got our statistics here. If you want to expand those out, so right now the blue numbers and the blue data points are your calibration data, and your red ones are your cross-validation data. So what we can do is go up at the top here. If I turn the calibration data off, it expands out those statistics so that you can get a more understanding of what's going on with your data. And as I mentioned earlier, our R-squared Pearson and our R-squared are very, very close to each other. So that tells us this is a pretty robust model. Once we have built our model and it's something that we are happy with, we can then test this on our new data. So I can come in under Tasks and Predict. I'm going to predict my regression. Using that first PLS, it defaults to 2 components. This is good. Now I want to do my test set. It does not include a Y reference. And we look at our process data, trying to predict that quality information. Oh, and I have an error. It is okay. It still works. It predicts. So what we get here is our predicted value and the expected deviation around those. So the tighter the bars, the more confident we are in the data. So this particular one, object 220, we're not quite as confident. It's sort of like your confidence limit around something. So we know that this is predicting at 49.9 plus or minus 5.6 of the same units. So if that's still acceptable for your particular application, then you can go with it. If that error is too large for your particular application, this might clue you to say, oh, I want to go grab that sample, take it back to the lab, do our traditional analytical testing, and see where it really lies. All right, so we'll close that for now and go back to the slides. So we talked about this a little bit already, but how do you interpret a model? So there's 5 steps really that you look at for your model. The first thing you need to do is determine how many components you want to take into account. Okay, this is very important because some of your graphs and statistics are very dependent on how many components or factors you're actually going to be using. The fewer components you can use as possible, the simpler the model and the more likely that you are not modeling noise. You want to look at the scores plot, see if your data is nicely distributed, see if there's any sample patterns, groupings, anything like that. Your loadings is going to be useful for understanding correlations between your variables and your response variables. Your predicted versus reference is where you check the quality of your regression model. This graph is one that you need to know, make sure that you have chosen the right number of factors before you start looking at this graph. Otherwise, you might be a little off in what you are looking at. And then your B coefficients. That is just your actual regression model. If you think back to your original linear regression, just a univariate where you've got y equals mx plus b. So these are those components. So your coefficients are your slopes, for example, for every single variable that you are using, as well as the offset. So how do you choose the number of components? Again, we look at our residual variance or our explained variance curves to see where a nice plateau is. If you aren't gaining any additional information as you add components, then you want to stop there. Also, if you see this validation curve diverging away from your calibration curve, that means that you're modeling noise. You're getting into unpredictability. You're losing prediction quality. So you want to stop before or at the point that that curve diverges away from the calibration variance. By definition, that calibration explained variance will trend to 100 or 0 in this case. So when that diverges away, stop. You need to be careful. You do need to choose enough components to describe your structured variation in your data. If you don't, then you'll also get poor prediction performance. That's when you have error in your model. And as you go and you keep adding more components, eventually you get to the place where you're getting estimation error, you're overfitting, you're trying to describe noise, things that are unstructured variations. And that is the point of multivariate data analysis, is you want to really highlight your structured variation and diminish your unstructured variation. Take a look at your scores plot. If you have different groups or similarities, you can see that as well. This particular data was looking at measuring a biological output based on the type of diet someone was eating. And you can see that the diets do sort of separate out from each other. And then you can make some interpretations about what that means by looking at this in conjunction with your loadings plot. You take a look at your loadings plots, you can see here that this EPA measurement, that's that biologic, is very close to this salmon diet variable. When things are very highly correlated, they will be very close to each other. So that means that as your intake of salmon is increasing, so is this response variable. Things that are on the other side of your correlation loadings, so like potato or your BMI, they are anti-correlated. So as BMI increases, this measurement is decreasing. In this case here, sex and BMI variables are correlated with each other because they're very near to each other, but they are anti-correlated with this hormone measurement. We take a look at our predicted versus reference plot. Again, don't look at this until you have made your decision of how many factors you're going to look at. What this is it looks at your predicted value, what your model is telling you your value is, versus your actual known value of y. And so a perfect response would be a 1-to-1, that target line, and with these data points very close to each other. And this is where we get our summary statistics that gives you the slope of that line, your offset, your correlation, R-squared, your error rates, bias, all of those things that when you're reporting to agencies or if you're writing a paper might be things that you include. Often RMSEs, those are the ones that you wind up reporting for a model. This is the equation for the error measurements for anyone who is interested in that, how it's calculated. So we have our predicted value minus our known value. We square that and sum those over all of the values we looked at and divide by the number of samples. And then we take a square root of that. Now this particular equation is for a test set of data. If you are doing a cross-validation, your denominator is actually n-1 because you are simulating a test set, so you lose a degree of freedom. And your RMSE-C for calibration is actually n-1 minus k, where k is the number of factors you are using, because you lose more degrees of freedom for everything that you are estimating from the data. Again, these are expressed in the same unit as y. That's very important to remember. So I have another example that we can look at that is going to be a spectroscopic example. So what I have here is some IR data. I'm going to plot it for you of different fuels. So this is near IR data of fuels. We're trying to predict, let me turn this off, predict octane content. Always plot your data first so you can see if there's anything going on, if you need to do any sort of pre-processing. This isn't too bad data, but as you can see, there are a couple of samples that are a little bit different than the other ones. If I turn my sample groupings on here and put my legend, so this is based on whether there's an additive in this. So some of our samples in this particular data set have ethanol added to them. And in this case, these two have ethanol added to them. If you remember your IR interpretation, this is the area that your OH bonds absorb. So that's why we're seeing a difference in them at that point. So what we're going to do is analyze partial least squared. We're going to use our training data, near IR spectra, to predict our octane amount. In this case, we do not want to weight our data because the variations from one wavelength to another are actually related to each other, and they're all on the same scale. They're on the same absorbance scale, so the differences actually have real meaning. Where in the previous case, the differences between a pH of 1 and a conductivity value of 2000 doesn't have any real significance, which is why we weighted those. In this case, we don't weight. We're still going to do a cross-validation, and this is the output we get. And I forgot to label this as spectra. By default, the unscrambler will make a scatter plot of your loadings and regression coefficients unless you tell it otherwise. It doesn't make a lot of sense when you look at spectroscopic data because these are your wavelengths versus each other, and it's just kind of a bit noisy. So what I'm going to do is I'm going to recalculate this. I'm going to label my spectra. If I right-click here, I can call it spectra. And now you will see when I run my PLS regression, that those plots will now be line plots. So this is much more easy to interpret when you're looking at spectral data. The peaks are analyzed or interpreted the exact same way you would a real spectrum. So once this starts to look like a lot of noise, it probably is noise. But again, first thing we want to look at is that explained variance. What we see here in factor 1, our cross-validation is really awful for factor 1, but then it's quite good for factor 2 and factor 3. This is really common when you have outliers in your data. And we can actually see them in this particular data set very clearly in our scores plot. I'm going to right-click, do a sample grouping based on the additive, and show that these two data points are the ones that have additive in them. So what I'm going to do is I can highlight those, I can mark them. Now you'll notice this is a good function in the unscrambler, is that when they are highlighted in one graph, they are highlighted in all of the other graphs as well. This allows you to do some more root cause analysis, make sure that you're removing the right things, and being able to justify removing those particular samples. So what I'm going to do is right-click and recalculate without those samples. Now I have a very nice, clear two-factor model. My regression coefficients make a lot of sense. We've got peaks in our CH bond region, so we're looking at branching, and a little bit over here in that OH and some of our other carbon-carbon regions. We can see in our scores plot that we follow our that we cover the whole space really well. And our predicted versus reference, make sure to check, yes, it's a two-factor model. Our statistics are really quite good. We can put our regression lines and the target line, and they are almost on top of each other. Now, one thing you might notice here is that our lower values aren't quite as well predicted as some of our higher values. So that could lead you to believe that maybe you want to do something a little different. You might want to do this first and separate things out into low, medium, high, Maybe it's the linear region is a little bit different in this lower range, so you may want to build a model that's more specific for that tight region. But if you're okay with this general error rate across the entire range, then you can stop here and that's fine as well. We can take a look at our scores plot too. If I right-click and do a sample grouping based off of our types, so this is going to be our low, medium, and high octanes. Create row sets. We can take a look that there is a nice little pattern between our two factors where our low values move towards our high values. So that's just a little bit of a confirmation that that's what's going on. So let's go back to our slides. We talked briefly about outliers there. You can have different kinds of outliers. They can be in the X data, which these particular ones were, right? So they had some spectral regions that were very different than the rest of them. You could spot those in both PCA if you do that on your data first, or in the regression. Your Y outliers, that can be if something's an extreme sample in your Y, like really low or really high. And you can, if you have more than one Y response, you can do a PCA of those to figure those out. You can also check the range of your Y using histograms to highlight where those are. And sometimes there is only a broken relationship between the XY relationship rather than one or the other. And there are some tools in the unscrambler for looking at that as well. This is just a list of sort of outlier detection tools. You can use this in your later as we go on. Perhaps we will do a webinar on outlier diagnostics itself as well. Again, so you start with your known data, you build a calibration, you deal with any outliers, you refine and validate and interpret your model, make sure that things make sense. And then once you have confirmed your model, you can do a prediction on that. If you have a reference value, you can compare that to your reference. If not, you have some statistics to back you up as well. Prediction's very straightforward once we have built our model. If you've done any pre-treatments, any new X measurements that you do will be applied when you use the prediction, and it will apply the same number of components. So you need to make sure that your components are set the right way. Now you still have to do some outlier detection when you do your prediction to confirm that your unknown samples are similar to your calibration samples. This is just an overview of what makes things an outlier. If something is similar, it's going to be reliable. If it's dissimilar, it's going to be unreliable. And these are sort of our tools we look at. How far from the center of the model it is, and how far outside of the model it is. If something is very far away from the center and has a high residual, very far out of that plane, then that's a huge indication that that is an outlier, and you either need to retest it or remove that sample from your production line or just from your data analysis. Just know that that's not a good sample. This is shown when you're doing the prediction. We showed that a little bit. If you have your predicted value, this is actually on that octane data as well. So when we are predicting new samples, we can see that our first few samples here, they have very tight error bars. They are similar to the calibration samples. We are really confident in that output. These last four have very high uncertainty. These are ones, I know this data, and those are ones that actually have that additive to them as well. So basically their residuals are very different because that X data, the spectrum looks very different. The values are not incorrect. They actually predict really well. We're just not as sure of them as we are the ones that look similar to our calibration data. So quick summary of advice. Prepare your workflow, state your overall objective. Don't look for correlations in your raw data by plotting endless columns of data. Do not mix your significance with relevance. If you have enough samples, anything can be found significant. Number 4 is a really key one. Everyone can fit a model to the data 100%. That's your calibration set. Really, you need to do a good validation to make sure that the proof is in the pudding. It will work for your new data coming in. And there's absolutely nothing wrong with concluding that for a specific case, there is no valid model. Sometimes the information just is not there. So what is a valid model? It really depends on the field you're working in. Whether you're in consumer science or sensory data, they're okay with a little bit less explained variance. If you get into the analytical field or pharmaceuticals, they're a little bit more strict and want things over 95%, even sometimes 99%. Okay, and this is why we need to validate the models to make sure that we are confirming our research hypothesis and you're validating your system as you repeat your studies. Going to skip that. This is just your general overflow again, and the different types of tools that you can use for this. And I'm actually just going to stop there. We've covered everything, and I want to make sure that we have time for questions. So if anyone has any questions, please type them in now, and I will answer them. Okay. I guess I covered everything really well this time. So if you have any questions that are burning and that come to you tomorrow or another day in the future, just email me here at hbrook@camo.com. I look forward to hearing from you and hope everyone has a good rest of the week.